I'm gonna just recap, okay, some of the concepts we discussed so far. Okay, so let us again consider this uncertainty principle. Okay, Heisenberg uncertainty principle. So in this case, I'm showing you several waves. Okay, so for example, in this case, we are only exciting one frequency or one wavelength here, and then we are basically showing like a summation of all these waves. But in this case, only one wavelength is activated, so obviously it's just same as that. But in the second plot, what we are showing here is we excited two. Okay, so one wavelength and another different wavelength wave, and then we are adding them up. Okay, so when we sum up, like this is kind of, you can think of this as kind of wave addition or interference or however you think, and then we are essentially kind of adding these two waves, and then this is like the resultant, the wave. Okay, and then we are gonna keep doing that. Okay, for example, in this case, we have four waves with four different wavelengths. Okay, so and then when we add them up, it's gonna show something like that. Okay, and in this case, we activated all the wavelengths with a different wave. We basically added all the waves with the different wavelengths. Okay, so as you see, basically the wavelengths is all different, and then when we add them up, it shows something like that. Okay. And then here is essentially kind of what we are going to talk about, uncertainty principle. So remember, what is the wave, de Broglie wavelength? Okay, de Broglie wavelength is defined as, do you remember? There is h over p, right? H is constant, and then what is the momentum? Momentum is mass times velocity. Okay, so in this case, when we sum up all the waves with the different wavelengths, we are going to kind of try to find out the location of the wave, and then we are going to kind of identify velocity of wave. Okay, so if you actually kind of look at this wave, can you kind of find out where the wave location is? Like a kind of intuitively looking at it, you can find that, okay, the location of the wave, you can maybe identify something like this, right? Because there is kind of strong peak there, right? And then, kind of it's easier to identify in this case, but what about velocity of wave? Velocity of wave is related to what? Wavelength, right? So in this case, but how did we construct this resultant wave? We were summing waves with different wavelengths. Do you remember? So we are essentially kind of adding waves with different wavelengths. What that means is that we were adding waves with different speed. Does that make sense? And then because of that, because we are actually mixing many waves with different speeds, it's obviously very hard to determine the velocity of wave, right? Because we are kind of adding waves with a different speed. Okay, so another way to kind of think about, maybe this is a kind of more obvious. Okay, you are picking wave with a certain wavelength. Okay, this is just kind of one wavelength. Okay, in this case, do we know velocity? In this case, do we know velocity? What's your thought? Yes, I mean, we know the wavelengths, let's say. We are picking just wave with a known wavelengths. So just following de Broglie wavelengths, if we know lambda, h is constant, m is constant, v is kind of determined, right? In this case, like if we pick wave with a certain, or with a known wavelength, then velocity of wave is essentially kind of determined, right? But what about location of this wave? Now it's hard to tell, right? Because it's basically like everywhere with the same amplitude. Does that make sense? So in this case, like velocity very well, but location, you don't know, right? But you apply this idea to this top one. Okay, again, in this case. What we are doing in this case, we were adding waves with the different wavelengths, right? with different velocities. As we add them up, the velocity is kind of mixed, right? We are essentially kind of adding several waves with different speed, and then velocity is going to be hard to find, but if you look at this resultant wave, there is actually kind of a certain peak up here. So in this sense, it's easier to find location of the wave, but you are sacrificing velocity. Okay, so this is kind of simple kind of demonstration of like how this Heisenberg uncertainty principle work. Okay, so again, just by looking at this, just demonstration, if you know the position precisely, you cannot know the velocity, and if you know the velocity precisely, you cannot know the position. Okay, that's a simple demonstration. But like another way to think about is just applying, the sigma x, sigma p should be equal or larger than h power 2, right? That is essentially kind of the equation that you can follow. But this is just simple demonstration, okay, about like how this Heisenberg uncertainty principle work. So do you have any questions on this? Hope this helps a little bit of understanding of Heisenberg uncertainty principle. Okay.
When you say position of the wave, do you mean position of the particle that's causing the wave, or do you mean like where the peaks are? What do you mean by position of the wave?
Yeah, position of the wave. So in this case, I mean, when we talk about wave, you can always think about that as also particle, because in quantum world, we always talk about wave-particle duality, right? So when you think about particle, they can be interpreted as a wave because of de Broglie wavelengths. So in the case, when we think about the location of this wave, you can also again think about that as kind of particle. Okay, so how can we find this particle, right? Then obviously this one has kind of a very high peak, right? And then if you think about this as kind of wavelengths or wave function, let's say, this wave function is translated to always probability density function, right? So think about this as kind of wave function, let's say. And then if this becomes probability density function, you know how to get probability density function, right? Psi star psi. So once you do that, you know that the probability of finding particle is really high around this position, right? And then in the sense, the location of this wave or location of this particle, you can safely say, okay, the probability of finding this particle is really high around, let's say, this position, right? So in the sense, you have a better idea in terms of finding the particle, right, location. But when you are doing that, you are essentially losing, accuracy of velocity because you have been mixing waves with different speeds. Yeah. Does that make sense? Yeah, so when we talk about this particle wave duality, it can be confusing, but that is essential kind of nature of this kind of small scale work, right? So when I say particle, you can think of that as a wave, and when I say wave, you can always think about that as also particle. Okay. So what does that mean? In quantum world, let's say let's consider just kind of bulk objects here, just rockets or balls. From classical approach, we've been always trying to find what is the kind of final location when the initial velocity and initial position is given, right? So for example, in physics, questions or mechanics, when the velocity is given and then for the given mass, and then if the initial location is given, we can always predict where this bulk object is gonna land, right? Where the final location is, or what is the velocity during the kind of the movement. So in the sense, it's easily kind of predictable for classical kind of object, right? This is essentially kind of what Newton's law tells you, okay? But what about in quantum world here? You cannot know location and velocity precisely at the same time, Okay, so what that means is that, for example, if you are dealing with this electron, okay, you can never predict where this is going to land. Okay, like for the final position, you will never know. Okay, so that is essentially kind of frustration, I guess, but that is essential kind of nature. Okay, so for bulk object, you can predict, what the final location is, but in this case, like for example, if you know initial position, you don't know what the initial velocity is. If you know initial velocity, you don't know what the initial position is. So in this case, how are you going to predict, during the course of this movement? Okay, so that is a kind of implication about Heisenberg uncertainty principle. Okay, so what that means is that this one again, this can only tell you about probabilistic event. Okay, in quantum world, it's not going to tell you about deterministic value. Okay. Okay, so then let us kind of look into this de Broglie wavelengths a little bit closer. Okay, this is like how it's defined, and then let us kind of look into oxygen molecules wavelengths. Okay, so oxygen molecule mass is given here 5.3 times 10 to the negative 26 power kilogram. And in this case, just for simplicity, we are going to use kinetic theory of gases. Okay, so what that means is that the kinetic energy of the molecules is related to this temperature. Okay, and 3/2 kb Boltzmann constant, and T is the absolute temperature. Okay, so from here you can also tell, higher temperature means higher velocity, lower temperature means lower velocity, right? I mean, that is just kind of what you guys can expect. And for this one, like if we use de Broglie wavelengths and then insert corresponding values, okay, we are going to just kind of replace this, and then we are going to get this de Broglie wavelengths of 0.1 nanometers. Okay, and then at room temperature, okay, or like the inter distance between oxygen molecule is typically about 10 nanometers. Okay, so what that means is that this de Broglie wavelength 0.1 nanometer is smaller than interparticle distance. So what that means is that this is safely can be assumed as particles. Okay, just the classical particles. Okay, classical particles. So like we don't really expect quantum behavior. Okay, because this wavelength is still a lot smaller than interdistance. Okay. So, and another way kind of to approach here is, like, can we actually make this oxygen molecule behave like quantum particle or quantum wave? How can we do that? That is essentially the question. Okay. So, like at this temperature, right, at this room temperature, it's not going to behave like a quantum particle. Okay, it's going to behave just like classical particle. But how are we going to make this as a quantum particle? Just look at the kind of expression here. Like what are the kind of tuning knobs that we have here? How can we increase de Broglie wavelengths? Lower the speed, right? That's exactly right. So in this case, we can lower the speed, then we can increase the wavelengths. Okay? But how can we lower the speed? Again, it's given here. Take a look. How do we lower the speed of an oxygen molecule? Decrease temperature, right? So if you look at actually kinetic theory of gases, the velocity is related to temperature. So if you lower the temperature, velocity is going to go down, and because velocity is going down, lambda is going to increase. And if lambda increase is such that this is comparable to interparticle distance or exceeding interparticle distance, you would expect kind of quantum behavior, right? So that is essentially kind of my argument here. So for example, so if you want to see quantum mechanical behavior using oxygen, you reduce velocity, okay, or in order to reduce velocity, you need to decrease temperature. So this one is kind of the trend for anything. So for example, like quantum mechanics or quantum computing is based on quantum mechanics, right? And occur very small scales, right? I mean, you have to deal with a small mass or a small scale object. And also, in order to increase that de Broglie wavelength, you have to actually push the temperature to very low temperatures. Okay, so extremely low temperatures. So in the sense, this is a kind of a, another good example. Okay, so I'm not sure if you guys heard about this Bose-Einstein condensation, but let us kind of take a look at this. Okay, maybe I'll move here. Let me see. Okay. Maybe I'll just directly click that. Oh, no internet connection. Oh, my password got expired. Okay, just 1 second.